So here we have a wonderful exam. It's Calc 3, Multivariable Calculus from Spring 2023. And this particular exam is the one that's the geometry exam. So we're going to do a lot of geometry and have a good time. So we start, as we always start, of course, write your name, because if you don't write your name, you won't get the credit. And now we're ready to begin. Problem 1. We're given the points A, B, C, and we're asked to do two things. So let's start with part A. Find the midpoint between A and B. So the picture here is we have point A, 2, 2, 0. We have point B, 0, 4, 3. And we're asked for the midpoint. Now, we can draw that. If we think of it as a line segment connecting these 2 points, the midpoint is the one that's halfway along the line. So it's the point right in the middle. Now, how do you find such a thing? Well, the nice thing is you do what you think you should do. You know, if I say, what's halfway between the numbers 5 and 9? Well, we'd say 7, right? And you do it by adding the 2 numbers and divide by 2. You average. And what you do is you just do it entry by entry. And so, for instance, the first entry, what's halfway between 0 and 2? Well, 1. You can find it by adding them together, divide by 2. Halfway between 2 and 4? 3. 2 plus 4 divided by 2. 6 divided by 2, 3. Halfway between 0 and 3? 1.5, or 3 halves. And there we go. There's the midpoint. That's it. That's it. Now, part B. Find the area of the triangle with vertices A, B, C. All right, so we are in 3-dimensional space, so we'll just quickly draw what's going on. So here we have our 3-dimensional space. We mark our points, and well, let's say A is here. We can say B is here, and maybe C is over here. All right, so those are our 3 points. Now, from 3 points, you can form a triangle, and you do it by you connect the points together. And so our triangle looks something like the following. And we can start asking questions, and our particular question is to say, well, how do you find the area of this triangle? All right, so we want to know, what's this area here? All right, well, what do we do? What do we do? Well, we start thinking. We say, well, have we encountered anything that involves area? Does anything cross your mind? Yeah, so it turns out cross products. Now, cross products have 2 cool features. The direction is perpendicular to what you start with. So when you're looking for perpendicular directions, that's the part you care about. The magnitude relates to area. In particular, there's this very cool fact that says the magnitude of the cross product of 2 vectors is the area of the shape where you take your 2 vectors and put them together, and then you have the opposite side. So it's a parallelogram. So it's the area of that shape. Now you might say, well, wait, that's not a triangle. That has 4 sides. A triangle only has 3 sides. So how does that relate to triangles? Well, the nice thing is that you can relate this to triangles very easily by doing the following. Namely, you cut it in half. Say, okay. So it's half a cross product. Great. So now we have a plan. We're going to find our 2 vectors. We're going to take the cross product. We're going to divide by 2. Life is great. So, which 2 vectors do we take? I mean, which one of these 2 do we take? And the answer is we don't take any of those 2. These aren't vectors. These are points. Make sure you know, when is something a point, when is something a vector? Because it matters. And if you use a vector as a point or vice versa, you will make mistakes and get the wrong answer. We don't want that. We want the right answers. They tend to get more credit. So what vectors are we looking for? Well, we're looking for the vectors that make up the sides. Coming back to here, really what happened is we had a u and v making the sides. So we say, all right, we pick two sides, meaning we pick a corner. Now it doesn't matter which corner you pick. You can pick any corner. I'll pick this corner. So I want to find these two vectors. All right, so vectors are changed. So to find a vector, we say, how much do you change? -1 to 2, that's a +3. 0 to 2, that's a -2. And, whoops, 0 to 2, +2. I have to be careful here. Order matters, right? We're going from here to there. 2 to 0, that's the -2. Yeah, be careful, be careful. Double check. It's easy to make small mistakes, and small mistakes cost us points. Oftentimes they cost us the most points. The big ideas we're okay with. All right, -1 to 0 is a 1. 0 to 4 is a 4. Again, I'm asking to change. 2 to 3 is a 1. All right, so these are our two sides, and we can even just mark them down here for reference. And 1, 4, 1. And we're going to take the cross product, and after we take the cross product, we'll worry about magnitude and all of those wonderful things. I like to take cross products by using the matrix and doing a determinant. So you put your I, J, K, your directions. You put in your first vector, 3, 2, -2. Put in your second vector, 1, 4, 1. All right, now go on your diagonals. There's two kinds of diagonals. There's the downward sloping. Those we're going to add. There's the upward sloping. Those you subtract. So I times 2 times 1 is 2I. J times -2 times 1, -2J. Here, we hit a wall, so you just wrap around. K times 3 times 4, 12K. Okay, those were our downwards. Upwards, 1 times 2 times K, 2K. But we subtract, so -2K. 4 times -2 times I. That's -8I. Now, but we subtract, so that becomes a +8I. And then 1 times 3 times j is 3j, but again, we subtract, so that's -3j. So altogether, well, 2 and 8 makes 10. -2 and -3, -5. And 12 minus 2 is 10. So 10 minus 5, 10. Now what if you're paranoid? Well, you can always do a quick check and say, look, do the dot products with the originals. So we get 10 times 3 is 30. 2 times -5 is -10, -20. 30 minus 10 minus 20, 0. Here you have 10 minus 20 plus 10, 0. Good, good. Now, I'll make a quick note that says, look, I can pull out a common factor. So this is really 5 times 2 minus 1, 2. All right, now, next, what do we do? Well, we have our cross product. We need to take our magnitude. All right, so our area will be 1/2 because we're only taking half of the parallelogram. Magnitude of 5, 2 minus 1, 2. Well, of course, you can pull the 5 out. So that's 5 over 2, square root. And then you square each entry. 4 plus 1 plus 4. Well, 4 plus 1 plus 4 is 9. Square root of 9 is 3. So this becomes 15 over 2, and that's your answer. That's good. All right. Now, on a side note, there were lots of choices that we could have made. You could have swapped this order. It would have changed the signs, wouldn't change the answer. You could have picked a different corner, would have changed the vectors, wouldn't change the answer. So there's a lot of built-in, yeah, there's some redundancy. Just find something and work it through. Be careful. The small things are going to be your biggest obstacle, so don't rush. Double check your arithmetic and your algebra. You're going to be fine. Number 2. A curve in three-dimensional space is given by r of t is t times I and 2/3 t to the 3/2 times k. Now, it's in three-dimensional space, but you might notice there's actually nothing in the j direction, so it's all happening in the xz plane. So it's secretly a two-dimensional, but that's okay. We'll forgive them for that. All right, so let's start with part A. Find the length, L, of this curve from t equals 0 to t equals 8. And your final answer should be an integer or a fully reduced fraction. Well, when they give us something like that, that says, look, this is a simplification command, which means we should anticipate the answer should be relatively simple. All right, so how do we find length? There's a couple of ways to find length. One of my favorites is to say, all right, I can find length by adding up the magnitude. Well, let me just say it this way. I'll call it speed. So if I integrate speed, dt. So speed times time is distance. So this is a small bit of time. And say, okay, well, that's a small bit of distance. And add them up, that's your total distance. But how does one find speed? Well, the answer is you take the magnitude of the derivative. So the derivative is the velocity. When you toss the magnitude on, magnitude of velocity is speed. And so there's our formula for finding our distance. Okay, good, good. Now, we just need to do our various pieces here. So what is r prime? Let's see, we probably have space to write it. So the derivative of t is 1, so we have an I. And here, 2/3 stays there, t to the 3/2, so the 3/2 comes down. 2/3 times 3/2 is 1, and so we're left with t to the 1/2 k. So in our case, we say, all right, our length is integral 0 to 8, because that's what we're told, 0 to 8. And then the magnitude of our I plus t to the 1/2 k. Well, all right, so to find the magnitude, it's the square root, and you square each entry. So 1 squared plus t to the 1/2 squared is t. And say, all right, good. So now you just have to integrate that. Well, okay, let's do this a little bit slow motion. Normally I would just say, aha, this is going to be da-da-da, but we'll go ahead and do it a little slowly. Why not? We have time. U equals t plus 1, du equals dt, and then what do we have? Well, we're going to update everything. So this will become u to the 1/2, because square root of u is to the 1/2 power. And writing it as to the power of half, it makes it more calculus friendly. dt is du, and then we have to update our bounds. So these are t bounds. It really says t equals 0 to t equals 8. We want u equals something to u equals something. So if t equals 0, u equals 1. If t equals 8, u equals 9. All right, good. Well, we're almost there. All right, integrate. U to the 1/2 will be u to the 3/2, then times 2/3. And then we have to go from 1 to 9. So this is 2/3 times 9 to the 3/2 minus 1 to the 3/2. All right, good news is 1 to the 3/2 is easy. It's 1. It's one of the reasons we like 1. It's very easy to compute. Now 9 to the 3/2. You can compute this in a couple of ways. One way you can do it is take 9 cubed, which is 729, and then take the square root of 729, which is, that's right, say it all together, 27. Okay, now, okay, that's not the way you really do it. When you think about it, your 3/2 says you're doing two things. You can think of it as you're cubing and you're taking to a 1/2, which means square rooting. So the question is, should you do the cube first or the square root first? Moral is, do the action which makes something smaller, and then do the action which makes something bigger. So, square root of 9 is 3. Let's do the square root first. 3 cubed is 27. 3 times 3 times 3. So, this becomes 2/3 times 27, subtract 1. Well, 27 subtract 1 is 26. And unfortunately, 3 doesn't go into 26. And so we end up with 2 times 26 is 52 over 3. 52/3. And there we go. All right, that's part A. Part B. Find the unit tangent vector to the curve at t equals 4. Now, tangent is pretty easy. So that's the r prime. But now there's a piece that says, but make it a unit tangent vector. So you say, okay, sure, no problem. So what we do is we say, all right, our vector t is going to look like r prime, that's the tangent, divided by the magnitude of r prime. Now we know what r prime is. We actually went through and computed it. So it's this vector I plus t to the 1/2 k. Now, what's the magnitude of r prime? Well, we did that too. It's this piece right here. So that's the square root of 1 plus t. And that's true for any value of t. Well, we need it at t equals 4. So we can plug in t equals 4. And doing that, what do we get? Well, we get the following. And we'll move it up a little bit here. So the unit tangent vector at time 4, well, we're going to have upstairs, we have I, square root of 4 is 2, so that'll become 2k. And downstairs, we have the square root of 1 plus 4, which is square root of 5. And we're done. So I plus 2k over square root of 5. And that's our answer. Now, there's other ways to write this. We could also have written this in the form where we do it component-wise. So in the first entry would be a 1 over root 5, that's the I, j, 0, and then the k would be 2 over root 5. These are both the same vector, just different ways to write it. And so be familiar with jumping back and forth as needed. All right, another problem done. Let's keep going. Number 3. Find the projection z of the vector x onto the vector y. Now, if you know the formula, this will be pretty quick. And if you don't, it will take you a little bit of time. But it's nice to remember things. So projection, this is associated with the dot product. And so it's going to come back to the dot product. We can rederive it. And since we have a few minutes here, let's talk about what's going on. So we have here the vector x. And what we do is we say, well, let's put the vector x and the vector y, put their tails together. And so, all right, so there we go. There's our x and our y. Now, when we talk about the projection, what that means is you can imagine casting a shadow. So this part right here is the projection of x onto y. In other words, this is our z. And so that's what we're after. Okay, good, 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 good. Now, we say, all right, well, what do you need? Well, we need a couple of things. We need to know the direction and the length, because that's what every vector has. Every vector has two things, direction and length. Now, the good news is we know the direction. It has to point in the same direction as y. That's what projection is about, saying, well, how much of it is pointing in this direction? So we say, all right, well, you can take the vector y and divide it by the magnitude of y, and then this is direction. We like to use unit vectors for direction. What's the length? Okay, so that's a little bit more. So if you put an angle theta there, and you say, okay, well, I can imagine there's a right triangle here because there's a right triangle here. That's why it's easy to imagine. And I know the length of the hypotenuse, then I can say that the length of the adjacent side is connected to the cosine, because cosine is adjacent over hypotenuse. And so it turns out that it's cosine of theta times the magnitude of x. So cosine of theta times hypotenuse is equal to adjacent. So here is our magnitude. Now, the great aha is people said, oh, if you stare at this formula, this almost looks like a dot product. And it's only missing a magnitude of y upstairs, and then it would be a dot product. So they said, okay, make it magnitude of x, magnitude of y, cosine theta. And then if I add a magnitude of y upstairs, I'll have to add a magnitude of y downstairs. And now the upstairs becomes a dot product. So it's x dot y. And the downstairs, it turns out, is also a dot product. It's y dot y, because secretly there's a cosine of 0, which is 1. So there you go. So this is the formula. If you remember this formula, this problem is easy. And if you don't, well, you just saw how to rederive it. All right, good. One of the ways to remember this, if you think about it, see how you have two y's upstairs and two y's downstairs? So the y's kind of cancel. You're left with an x, but the direction has to be in the y because it's a multiple of y. So it feels right, right? Yeah, it's got a good feeling. It's got a good feeling. It's kind of weird to talk about. Yeah, math feels right. Okay, so here we go. Now we're ready. So we're going to talk about our x. We'll write that down for reference. So x is our vector 1, 2, 4. And y is our vector 3, minus 2, 5. So we're going to take x dot y over y dot y times y. All right, so x dot y. So remember, you multiply the corresponding entries and add. 1 times 3 is 3. 2 minus 2 is minus 4. 4 and 5 is 20. Downstairs, y dot y. So 3 times 3 is 9. Minus 2 times minus 2 plus 4. 5 times 5, 25. And then you just copy 3 minus 2, 5. All right, 23 minus 4, that's 19. Then here we have 13 plus 25, that's 38. 3 minus 2, 5. Or if you like, that's 1/2. 3 minus 2, 5. Because 19 divided by 38 is 1/2. All right, so that's part A. Okay, now part B. Suppose we just found z. What is the projection of z onto y? Now remember, we said the projection, we didn't draw it, but it's this vector right here. That's z. Okay, so now the question is how much of z is pointing in the direction of y? And the answer is it's all pointing in the direction of y. So z and y are parallel. And when you project onto parallel vectors, well, you don't change your vector because you say, look, I'm already pointing as much as I can in the same direction as you because we're pointing in the same direction. Or secretly might be pointing exactly opposite, but that's another story. And so what's the answer to this one? Well, the answer is it's z. That's it. So this part B, is testing your geometrical intuition. Do you understand what a projection looks like? And so yeah, we have that. No problems. All right, so there we go. We've done projection. We've done our dot product problem. Well, we might have one or two more. Who knows? Let's find out. Number 4. An asteroid follows a path, and its r of t is 5 minus 2t, 7 plus t, minus 1 plus 2t. Now let's pause. Do we see what this path is? Look at the entries. They're pretty nice. 5 minus 2t, 7 plus t minus 1 plus 2t. That path is a straight line. So that's good to know. All right, so an asteroid is going on a straight line through three-dimensional space where distances are measured in parsecs. And all right. T is time in years. Earth happens to be located at this point, 6, 4, minus 2. All right, part A. Find the minimum distance from Earth reached by the asteroid. Include units. Now, because we need units, we automatically know, well, it's a distance, and distances are measured in parsecs. So it's like, okay, we know whatever we write down, we write parsecs after it, and even if we get everything else completely wrong, we'll get the units part right. So hey, we're going to get something out of this because we want to get everything, so we should start with something. All right, minimum distance. Now, there's lots of ways to do this. And so we could do this problem like 3 or 4 different ways. So I'm not going to say like do the problem this way. I'm going to talk about the way I would do this problem. And I'll give you some options as we go along. Now, we already mentioned it's a line. That helps tremendously. So here's our R. And we have this point, 6, 4, minus 2. So what are some options? Well, one option is you could pick a point on this line, and then you could say, well, what I'm looking for is I could find this vector, and then I can find that vector. And how do you go about doing that? Well, you can find this vector, you can find a projection, and then you could say, well, once I have those two, I can take an appropriate difference and get that one. So you can find this vector, do a projection, and then subtract the projection out, and life is good. You can also say, like, all right, if I'm after this, this I can represent, if this is theta, and this is a vector, well, let's give this a name for a second, u. Well, I could say magnitude of u sine theta. Now, the dot product is related to the cosine, but the cross product is related to sine. And so by an appropriate cross product argument, you can actually find what you're looking for. And indeed, there's a generic formula that finds the distance between a point and a line that's based off of the cross product. But I'm so old, I forgot it. So I always just say, look, whenever I run into a situation, I'll make it work. So that's an option. Now, another option you can do is just be like, look, I can set up literally, here's this point, 5 minus 2t, 7 plus t, and minus 1 plus 2t. And now what I'll do is I'll find the distance here, and I'll just solve an optimization problem. So use the Calc 1 tools, and that will get you the right answer. Now, what am I going to do? Well, I'm going to do something that I like, is to say, well, I'm after a particular point. And so I'm looking for that sweet spot. I'm looking for this point right here. Now, what makes this point special? Well, namely, it's going to form a right angle. So the great aha is if I look at the vector from this point to 6, 4, negative 2, well, okay, how do you find such a vector? You subtract. So I'm going to take 5 minus 2t, subtract 6. So I want minus 1, whoops, minus 1, I keep saying minus 1 and putting in a comma when I need to do minus 1 minus 2t, right? 5 minus 2t, subtract 6. 7 plus 2t, subtract 4. That's going to be 3 plus t, right? 7, subtract 4. Minus 1 plus 2t, subtract minus 2. That's going to become a 1 plus 2t. All right, so that's an arbitrary vector here. So this is, we could call this u. Here's our u. And we want that this is perpendicular to this line. Now, what's the direction of this line? We can read it off. it's the coefficients of t. So -2, 1, +2. All right, well, how do we know when two things are perpendicular? Well, the answer is their dot product is 0. So here we go. We're going to take -1 minus 2t, 3 plus t, 1 plus 2t, and do a dot product with -2, 1, 2, and set it equal to 0. And we're going to solve for t. And once you solve for t, you'll have found this point. And we'll come back to it once we actually finish that step, right? All right, so this becomes a 2 plus 4t. That's the first one. And then we have 3 plus t. That's the second one. And then we have another 2 plus 4t. Set this equal to 0. And, well, my t there looks an awful lot like a 2. Be careful. You want to make sure you can read your own handwriting. So 4t plus 4t makes 9t. 2 and 3 and 2. Well, that makes +7 equals 0. Or, if you like, t equals -7/9. That's a weird number, but that's all right. Now, what happens next? Well, when you plug in t equals -7/9, that will say where this point is. Well, what do we need to do? We need to find the distance from this point to that point. And how do we do it? Well, we can find the vector between them and find the magnitude. Well, good news. There's a shortcut. I can take this -7/9 and plug it into there. All right, doing that, we end up with -1, and then -2 times -7/9, that's 14/9. And then we have 3 minus 7/9, and then we have 1 and minus 14/9. And these are weird numbers, but that's all right. We can pull out a ninth. So if we do that, 1/9, pull it all the way out, and then we'll have -9 plus 14. So that makes a +5. Here we'll have 27 subtract 7. That makes 20. And here we'll have 9 minus 14, which makes -5. So again, we can pull out 5. So we have 5/9 times 1, 4, -1. All right, we're in our home stretch. So this is this vector on that side. We need a distance. Distance is a number, not a vector. And so, therefore, we take the magnitude, and doing that, we'll end up with 5/9, 1, 4, -1. So that will give us 5/9 times the square root of 1 plus 16 plus 1. Now that's square root of 18. And the square root of 18, you can pull out a 3, and then you're left with square root of 2. When I say pull out 3, it's 9 times 2, square root of 9 is 3. And so if you pull it out, you can cancel with the 3 downstairs, so we end up with 5/3 square root of 2. Whew! Wow! That's a lot of work, right? Well, like I said, there's other ways to do it, and regardless of which way you do it, you will still end up with 5/3√2. Unless, of course, you make a mistake. Now, I noticed I wrote this down. What did I forget to do? I forgot to put in my units because the problem asked for units. And so I really should have written down 5/3 square root of 2 parsecs. Yes. Now we're cooking. Make sure you get all those points. Don't want to lose any small points. All right, now on to part B. What is the speed of the asteroid when it reaches the minimum distance? Now, speed, remember, that's found by taking the magnitude of r prime. That's just r prime is velocity, magnitude of r prime is speed. Well, r prime, when you take the derivative, let's pull it back down, derivative of each entry, -2, 1, +2. Like, what? That's easy. It is. So that means we're taking the magnitude of -2, +1, +2. All right, well, that's the square root of 4 plus 1 plus 4, which square root of 9 is 3. Now you might say, wait, where's the t part? It turns out it's always moving at the same speed. So this is a case where the speed is constant. And so that's okay. So since the speed is constant, well, that means it's constant at the, it's that same constant when it reaches that minimum distance. So the answer is 3. We haven't circled it yet because include units. All right, so what do you need? Well, speed, you need a distance measurement and a time measurement. So our distance measurement is parsecs, our time is years. So we're going to have 3 parsecs per year. And there we go. There we go. All right, good. Whew, that one turned out to be a little bit trickier than I was hoping, but we got through it. We should have at least one or two that makes us a little nervous, right? We have to work a little bit. And well, I guess this is one of those one or two. All right, on to the next one. Number 5. Each equation in Cartesian coordinates on the left matches an equation in cylindrical or spherical coordinates on the right. And draw a line connecting the equation in Cartesian coordinates to its corresponding equation on the right. Okay, so we're playing a matching game. Now you have to think about what things are and think about how to represent them. And it can be a little bit tricky here. I'm not going to say like, aha, things are going to be totally obvious and life is good. It's all going to be just instantaneous, because it's not. And you have to understand how everything fits together. So let's see if we can't reason through a couple of these things. Well, let's start maybe here. Sine theta plus cosine theta is r minus z. Now this is cylindrical. We can tell that right away because what do we see? Well, we see an r and a z together. Now, when we're going from cylindrical back to Cartesian, it's a little bit easier to do that. Well, we want not sine theta, but r sine theta. So we say, okay, well, let's imagine we multiply everything by r. R sine theta, r cosine theta, r squared, and zr. Then that would leave us with an x, a y, an x squared plus y squared, and a z, and a square root of x squared plus y squared. We say, okay, is there anything that has those pieces in there? Well, here's an x and a y. Here's an x squared plus y squared. Here's a z times square root of x squared plus y squared. It's all the pieces, but it's just been rearranged. So I say, perfect, perfect. Now you might say, well, wait, why not this one? Well, because you're missing lots of stuff. You don't have your x and you don't have your y, and so that's not going to work. So there we go. All right, we got our first one matched. Okay, how about our next one? Rho equals 2 cosine phi. Now this one is definitely spherical. Now this is, we're not getting any points for this, but it kind of helps us get going. So all right, what can we do? Well, again, I would multiply both sides by rho. So rho squared is 2 cosine phi times rho. And rho squared is an x squared plus y squared plus z squared. Now, what is rho cosine phi? Well, you kind of need to know what's going on with your system, right? So what's happening here is if we think about what phi is, so here's our point. We have our rho, and we have our angle phi. So what's going on is what's the, sorry, I want to draw a line same here. When we look at the cosine, it's the side adjacent. So the side adjacent is the z-axis. So rho cosine phi is z. So we're looking x squared plus y squared plus c squared, and we're looking for a z. Well, we're looking for a 2z. Do we have anything with those pieces? Yes. And match. All right, good. Okay, well, what's next? 2 sine phi is minus cosine phi. The phi tells us we're spherical. And now I want to multiply through by rho. Okay, now we talked about cosine phi times rho. That becomes our z. What about sine of phi? Well, sine of phi times rho is going to be this. So cosine finds your adjacent, which is z. Sine finds your opposite, which is r. Or if you like, it's the square root of x squared plus y squared. So we want 2 square root of x squared plus y squared and a minus z. Now, if you look, if you move the z across, you get z and 2 square root of x squared plus y squared. So we have a match. All right, lots of crossings going on right there. Well, okay, can happen. No worries, no worries. All right, well, 2 to go. Okay, well, maybe let's just jump ahead. R equals 2 cosine theta. Now this is great, because what's going on here? Well, what we have is cylindrical. We have r. All right, well, what's going on? If we multiply both sides by r, that's r squared is 2 cosine theta times r. Now r cosine theta is x. So we end up with x squared plus y squared equals 2x. Well, there's an x squared plus y squared. Move the 2x across. And so there we go. Wow. All right. One left. And now, by process of elimination, we know what's going to happen. It's going to do that. But even if we didn't have process of elimination, we could multiply here. Now this is spherical, and what gives away spherical is the phi. Multiply by your rho, and then you see, aha, rho cosine phi is your z, rho sine phi is your r. R sine theta is y, r cosine theta is x. So you have z, x, and y. And just rearrange. All right, and there we go. Wow, that's a real workout. This one can be challenging, especially if you're not comfortable with your coordinate systems. But all right, let's go to part B. For each equation, circle the one-word description of its graph. All right, wow, actually, these look really familiar. They're the ones we just talked about, right? Now, some of these are pretty plain. Yeah, so the last one is pretty easy to spot. That's a plane. AX plus BY plus CZ equals D. What about some other ones? Well, here you have your x squared minus 2x plus y squared. What don't you have? You don't have z. When you don't have z, it means you're going to just take whatever that shape is, it turns out to a circle, and copy it straight up and down. So whenever there's a missing variable, that corresponds to a cylinder. So, all right, that's good. We've gone 2, done pretty quickly. Now here we have z plus 2 times the square root of x squared plus y squared. Now what's that? Well, if you look at the formula, you can actually come back here, right? Let's see, which one? Oh, it's a little bit hard to see what that one is, so let's talk about it. So the square root of x squared plus y squared, z equals square root of x squared plus y squared, it's a cone. And if you rewrote this in terms of cylindrical coordinates, this is z equals minus 2r. And so what it says is that as you increase r, your z is going to, in this case, go down at a constant rate. This is a cone. It's an upside down cone. So, all right. Now, x squared plus y squared plus z squared minus 2z equals 0. What's this? Well, if you see the x squared plus y squared plus z squared, that makes you think something like a sphere. Well, because it is a sphere. And you can even talk about what the sphere is. If you complete the square by adding 1 to both sides, you'll get x squared plus y squared plus z minus 1 squared equals 1 squared, which is indeed a sphere. All right, good. And then you have this last one. X squared plus y squared minus x minus y equals z square root of x squared plus y squared. Ugh. Is it a plane? No. You have squares. Is it a sphere? No. That square root messes you up. Is it a cylinder? No. You see all the 3 variables. Is it a cone? Well, it has the square root of x squared plus y squared, but it has all these other things. No. What is it? No name. No name. So that's just, it's a weird surface that we don't have a good name for. At least not a name we've talked about. And all right, so there we go. There's our answers. Whew, that one was really good. Workout. I don't know if I'd like to see this on a test. I think I'd panic a little bit if this was on a test. But in terms of working out our understanding, not bad. Number 6. Consider the curve given by, here r of t, parametric, 5t cosine 2 pi t, t squared plus 3. Find the tangent line to this curve at 5, 1, 4. Notice this is a point, and so we say, okay, how do you find a tangent line? Well, we need a line. So here's our point, and notice which value for t works. Well, let's look at the first entry. When does 5t become 5? Well, just at t equals 1, so we say, aha, so we're looking at t equals 1. So we're in good shape. We have our point. We know when the tangent line would occur, in other words, the right time. What's the last thing to make a line? Direction. So the direction, that's found by taking r prime. And in particular, because we know what time it is, it's going to be r prime of 1. All right, well, let's just take r prime of t and see what that would be. We'd have 5. And remember, the way you take derivatives, one entry at a time. Derivative of cosine 2 pi t, well, chain rule, derivative of cosine is negative sine. And then times by the derivative of the inside, so 2 pi. And then in the last entry, derivative of t squared plus 3 is 2t. 2t or not 2t? That is not the question, because it's definitely 2t. So we plug in 1. What do we get? We get a 5. Sine of 2 pi is you've gone full circle. You're back to where you started. So sine of 2 pi is 0. And then 2 times 1 is 2. So 5, 0, 2. All right. Now, I like to write my curves parametrically. Sorry, I like to write my lines parametrically, even my curves too. And so I'm going to write it in the following format. X, Y, Z. I'm going to remember that I need to have a point. And then I need to have t times direction. All right, so there's my pieces. And my point is 5, 1, 4. My direction is 5, 0, 2. Or if I just clean that up, I get x is 5 plus 5t. Y is constant value for 1. And z is 4 plus 2t. All right, so we're done with part A. And that was worth 8 points, so part B should be pretty quick. Okay, so now what is part B? At which points, could be one, could be many, does the tangent line from part A intersect the xy plane? Now, if we're thinking geometrically, what is the xy plane? Well, the xy plane is this part right here. So this is the xy plane, and this is z equals 0. So the question is, okay, when is z equal to 0? So we'll set the z coordinate, 4 plus 2t equal to 0. And then we say, oh, well, that's the same as saying t needs to be negative 2. So plug in negative 2. We'll see that x is 5 minus 10, y is 1, z is 0, which becomes negative 5, 1, 0. And there we go. We're done with this one. There's still one more. Our last problem. There are two planes, 2x minus y plus z equals 0, x plus y plus z equals 6. And if I have two planes, they intersect in a line. So there's a line of their intersection. Give an equation of the line. Now, you'll see they use the word un because there's many possible equations. So I'm kind of surprised they asked this question, because there's so many correct ways to express the answer, but that's on them. For us, we just have to find one of them. Now, there's a couple of different approaches, and we'll do this in at least two ways. So here's one way I like to do it, and probably the way they want you to think about it, which is to say, well, if I have these two planes, and I'm thinking about what do their intersections look like, and let me just, how do I find the line? Well, I need a point and a direction. So let's go to direction. So for the direction, I say, well, it's a line that's in the first plane, and it's a line that's in the second plane. So I need to be perpendicular to the normal vector of the first plane. So I need to be perpendicular to the vector 2 minus 1, 1. And I need to be perpendicular to the direction vector of the second plane, 1, 1, 1. Well, how can I find something perpendicular to two things simultaneously? Cross product. So this is what I think they wanted you to do. Take a cross product. All right, good. Let's just do that. So here we go. 2 minus 1, 1, cross 1, 1, 1. We have our I, J, K, 2 minus 1, 1, 1, 1, 1. And what do we have? We have I times minus 1 times 1, that's minus I. J times 1 times 1 is plus J. K times 2 times 1 is 2K. Okay, going downhill. Subtract, going uphill. 1 times minus 1 times K is minus K, but we're subtracting. So we add K. 1 times I is I, but we subtract I. And 1 times 2 times J is 2J, but we subtract 2J. So we end up with a minus 2, minus 1, 3. Now, quickly double check. Dot products. Minus 4 plus 1 plus 3, 0. Minus 2 minus 1 plus 3, 0. Good. So it's definitely perpendicular to both. Here is our direction. How do you find a point? Now, this is where we come into something interesting. We just need to find any point at all. Any point. So the reason that this becomes interesting is we have two equations, 2x minus y plus z equals 0, and x plus y plus z equals 6. Two equations, but three unknowns. So that feels like it's out of balance, and that's why there's a line. But now, here's the thing, is you can make a choice. You can choose any one of the variables to be any value that you like. So, make a choice. All right, choose x equals 0. Why? Well, because I want to get rid of the x, so I will. If you choose x equals 0, then what you'll do is you'll get down to minus y plus z equals 0. and y plus z equals 6. Now the first equation becomes really easy. This says that y equals z. And once you know that y equals z and that y plus z equals 6, well, that says y plus y equals 6, or that y has to equal 3. So what's our point? 0, 3, 3. Now, could you have gone this point in another way? Well, I should say you could have gone a different point by making a different choice. I could have chosen y to be 0. Could have chosen z to be 0. I could have chosen x to be 100. Just make a choice to get you down to 2 equations, 2 unknowns, leading you to a unique solution. Now, at this point, we have our point, and if you're nervous, you can always come back and plug it in and just verify these are, in fact, points on the planes. So 0 minus 3 plus 3 is 0. 0 plus 3 plus 3 is 6. So point, direction, and we do, similar to the last problem, we make our parametric lines. X equals y equals z equals points 0, 3, 3, direction minus 2t minus t plus 3t. And done. All right, so there we go. There we go. Now, the reason why that there's many possible ways to express this is there's many possible points. Change a different point, you change the formula, you don't change the line. As long as it's any point on the line. You can even scale the direction of the line, still the same line. Now, I said we do this in another way. I think we have a little bit of time. So let's try to do it a second way, just to say it could have been done this way. All right, well, what can we do? Let's start with what we know. We know 2x minus y plus z equals 0, and x plus y plus z equals 6. Now this is 2 equations, 3 unknowns. What we can do is do a little bit of cancellation. So for instance, if you add, what do you get? You'll get 3x plus y plus 2z equals 6. Not plus y. The y's cancel. 3x, no y, 2z equals 6. Or, if you like, 2z equals 6 minus 3x. Or, you could say z is 3 minus 1.5x. Oh my gosh, I feel like an engineer now. I put 1.5. All right, but that's okay, all right. Now, we have something for z. Let's take that and plug it into our first equation. Okay, so 2x minus y plus 3 minus 1.5x is equal to 0. Well, what does this tell us? If I move this y over to the other side, it tells us that y is 3, and then we have 2x minus 1.5x, which is plus 0.5x. Okay, so what do we have? Well, we have one more thing, which is we have x. And so now what we'll do is we'll let x, that'll be the thing that varies, t. What is y? 3 plus 0.5t. What is z? 3 minus 1.5t. And there we go. That's also a solution. And if you look, you'll see, in this case, we ended up with the same point. And if you look at the vector that we have, here it's minus 2, minus 1, 3. Here it's 1, a half, minus 3 halves. They're two scaling the same vector. So you can use geometry, or you can just say, oh, look, I'll just take the 2 equations, solve for y and z in terms of x becomes t, and then life is good, and I have what I need. So there's options. Which way you do it is up to you. As long as they don't say do it specifically this way, you can do it any way you want, and you're fine. So, all right. We had our fun with geometry. I hope you do well. I believe in you. You're wonderful, and let's be great. And I'll see you soon. Bye.